As the title suggests, today I'll be making diethyl ether, a highly volatile organic solvent formed from two ethyl groups linked by an oxygen atom. It's widely used as a laboratory solvent and has historically served as an anesthetic and engine starting fluid. Nearly every chemistry lab keeps a bottle on hand, and despite its importance, it's surprisingly simple to make from just anhydrous ethanol and concentrated sulfuric acid, which in my case comes in the form of drain cleaner. For reference, here are the quantities of every reagent used in this synthesis. To begin, I prepare my round bottom flask, and into it I add 45 ml of anhydrous ethanol. I then measure out 40 ml of sulfuric acid, and at this point I realize I don't have a glass thermometer available to monitor the reaction, so I quickly prepare a sealed borosilicate glass tube to isolate and protect my digital thermometer from the sulfuric acid. I then fit a 24x40 thermometer adapter, place it into the flask, and begin cooling the ethanol in an ice bath. Meanwhile, I attach an addition funnel to the top of the flask and fill it with the sulfuric acid. After 10 minutes, the ethanol reaches approximately 5 degrees Celsius, and I begin adding the sulfuric acid dropwise, carefully controlling the addition rate to prevent the reaction temperature from rising too quickly. Once the solution is thoroughly mixed, I add 10 grams of sand previously boiled in sulfuric acid to remove impurities. The sand acts as a boiling aid, providing nucleation sites that help prevent bumping during distillation. Afterwards, I recharge the addition funnel with 125 ml of anhydrous ethanol and proceed to assemble the fractional distillation apparatus. The receiving flask is thoroughly dried and placed in an ice bath. I then attach a tube to the vacuum adapter and route it outside so any escaping ether vapors are vented out of the building. At the last second, I add a stirring bar and set the heating mantle to 130 degrees Celsius. The reaction is typically carried out between 130 and 150 degrees, where diethyl ether formation is favored. At temperatures above 150 degrees, dehydration increasingly produces ethylene gas as the major byproduct. In this reaction, sulfuric acid acts as a catalyst, temporarily converting ethanol into a more reactive intermediate. A second ethanol molecule then attacks it, forming diethyl ether, while the sulfuric acid is regenerated and can repeat the cycle again. Once the first ether vapors begin ascending the fractionating column, I gradually add the ethanol and maintain an addition rate that matches the rate of diethyl ether production. From this point on, I had to constantly monitor the reaction temperature, the heating mantle setting, and the balance between ethanol addition and ether production, as several positive feedback loops kept pushing the reaction out of its optimal range. Honestly speaking, this felt like driving a manual, but on a heating mantle. Anyways, after 2 hours, I had my crude yield of ether. I immediately set it up for a second fractional distillation, this time placing the heating mantle thermometer probe at the top of the fractionating column, so that the thermostat would only let through vapors with a boiling point below 50 degrees Celsius. At the same time, I prepare a drying agent by baking 25 grams of calcium chloride at 200 degrees centigrade, driving off any absorbed moisture before it's used to dry the ether. Once the second distillation is complete, I break up the anhydrous calcium chloride and add it to the ether. The calcium chloride absorbs any remaining water and residual ethanol. Since this process is strongly exothermic, it can easily boil off some of the ether, so it's best carried out in an ice bath. Ether vapors are extremely flammable and can ignite if they come into contact with a sufficiently hot surface, spark, or open flame. Anyways, I then distilled the solution one final time, and as you can see here, the yield was quite low, only about 60 milliliters, or roughly 40% of the theoretical yield, which is normal when working on such a small scale. This is most likely because the product had to pass through 3 separate distillations, during which a noticeable amount of ether simply escaped without condensing. For storage, I wrapped some PTFE tape around the bottleneck to improve the seal. Diethyl ether is commonly sold with peroxide inhibitors because prolonged exposure to air can lead to the formation of hazardous ether peroxides. Since I don't plan on storing this ether long term, I'll likely dispose of it within the next few days. Light can also accelerate peroxide formation, so I wrap the bottle in aluminum foil to keep it in darkness and reduce that risk. I now wanted to perform a quick quality check by using an evaporative cooling test, in which a thermometer wrapped in a solvent-soaked paper towel cools as the liquid rapidly evaporates from its surface. And finally, I wanted to simply burn some of the ether. Anyways, I hope you enjoyed the video, and see you next time.